Build a network of AI agents, scale it up indefinitely, and watch it solve any complex problem. That assumption drives the push toward multi-agent systems. Developers are rapidly moving away from single chatbots. The operating logic assumes that networking a dozen identical agents together produces an exponentially smarter system. Popular frameworks organize these agents into what the industry calls a flat crew. A small pool of identical language models is differentiated with a few text prompts and placed into a single horizontal communication loop. The system quickly chokes on its own output. Adding a second or third agent yields improvements, but adding a sixth or seventh causes performance to abruptly stall. The agents start generating noise and talking over each other in an endless loop. In multi-agent networks, pure horizontal scaling directly equates to increased chaos. The ODTOE framework diagnoses this exact failure point. The core problem is a structural flaw identified as low observer dimensionality. When identical agents collaborate without a hierarchy, the communication channel between them degrades. They end up flooded with low-quality information and struggle to filter the signal from the noise. This chart tracks joint coherence against total agent count. The collective effectiveness of a flat network scales up initially, but hits a harsh, unyielding ceiling around 5 to 7 agents. Flat crews have a hard mathematical upper bound. Breaking through this intelligent ceiling is not a matter of adding computing power, but a mandate to reorganize the geometry of the system to support vertical depth. Nikola Tesla maintained a lifelong historical obsession with the numbers 3, 6, and 9. Stripping away the esoteric mythology surrounding his notes reveals a structural pattern that aligns with modern network topology. ODTOE identifies 3 as the minimum count for a stable feedback loop between a strategic top, a tactical middle, and an operational base. 6 provides each level with a dedicated partner to manage feedback, and 9 allows for internal cross-checking within each tier. These specific numerical ratios serve as the architectural blueprints for a structurally sound intelligence network. The ODTOE framework replaces the flat plane with a fractal pyramid. The top layer consists of 3 strategic agents. These nodes maintain high focus and avoid raw data, functioning strictly to provide direction and mandates. Directly beneath them, the architecture supports 6 tactical agents. This layer acts as a bridge. They continuously check their operational plans against the specific strategic mandate issued by the node above them. At the foundational base of the pyramid, we find 9 operational agents. This data-rich layer handles execution. Grouped in 3s, these agents explicitly cross-check their own outputs to catch errors before routing the final reports upward. True system power derives from distinct, specialized roles interacting vertically within a structured hierarchy, rather than identical clones working horizontally. This static architecture relies on a dynamic exchange to remain stable, utilizing what the ODTOE model calls pi closure protocols. These are essential feedback loops connecting the distinct layers. Data particles flow upward from the operational level. Simultaneously, strict validation pulses flow downward, constantly realigning the execution layers with the core strategy. This explicit, continuous loop of upward execution and downward closure is what prevents the AI from drowning in its own noise. Real-world benchmark data from 2025 and 2026 validates this theoretical topology against traditional frameworks. This chart visualizes performance on long-horizon software engineering tasks, specifically the SWE bench verified tests. Running on equal compute budgets, the 369 framework scored exactly 14 percentage points higher than the best flat crew baseline. That advantage widens when measuring adversarial robustness against prompt injection attacks. In comparing hallucination catch rates, standard flat crews intercept injected errors about 35% of the time. The 369 tactical layer catches those exact same injections 85% of the time. Structural closure layers catch system hallucinations before they can propagate into a network-wide failure. For practitioners building multi-agent products, engineering effort must shift away from tweaking individual agents and focus entirely on designing the protocol. In a properly structured hierarchy, the protocol acts as the multiplier. The individual AI agents are simply the multiplicands. An unstructured agent pool creates an unstable geometry destined to collapse. A 3-tiered pyramid locks that information flow into a stable engine. Without a mandatory structural topology, an AI system functions as an inverted pyramid waiting to fall. True multi-agent intelligence demands a fractal architecture.